So this class, and again, sort of this early portion of this course is really about trying to, equip us with the sort of categories of things that engineers need to think about. Obviously, last week we thought a lot about sort of problem and one identifying appropriate problems and beginning that process of researching and trying to understand the details of that. All of these things we sort of see once here in sort of the lecture portion. We do some activities, but we will mostly do our sort of heuristic learning, sort of learning by doing, in the realm of our final project, trying to apply, picking a problem that we want to work on for the semester, trying to understand all causes and effects and trying to model or simulate why that problem exists so we can begin to uh, test different solutions. And the next phase, and usually trying to go from what is the problem, am I equipped to solve it, how do we analyze or understand why it exists, is really one about trying to understand the assumptions and constraints we're given for any particular project. In many cases, we are often given constraints of things that we know we must adhere to. Engineers, of course, must adhere to the laws of physics and chemistry and biology, and that's one thing that most of your non-engineering courses equips you with, those rules or those fundamental laws that act as, of course, constraints on what we do. But very much more, and where engineering comes in as an applied science, is very much we're not given all the information we need to solve a problem exactly. We have to make some assumptions, and there's better and worse assumptions we can make. And to think about this idea and to practice this process of trying to refine assumptions and work within constraints, we're going to be answering a solicitation from the so-called Department of Penny Transportation. Try to build them some vehicles according to their requirements. So engineering is, of course, a very empirical science, meaning that we measure things, we deal with a quantitative analysis of how something will perform, how large a problem is, so on and so forth. And ultimately, we would love to be able to sort of sit in sort of our little sandbox and play and build and be able to sort of test as we go and to sort of make sure that every time we make a design change, we can verify that it does work. Uh, However, as we move from sort of more smaller, malleable, low stakes type of engineering, things that we're going to be doing in this class so that we have abilities to practice. In many of our engineering cases, we really don't have that same sort of liberty to test a sort of wonky, half thought out design. In many cases, we have really one chance to make sure that the one design that we've picked, built, constructed, permitted, told people about, funded, does work exactly or within reasonable bounds of what we expected. Very much that's often given as an issue of cost, safety, or time. Not super recently, but within sort of the last few decades, the city of Boston completed construction on the Zakim Bridge, which spans the Charles. And of course, that large, very, very wonderfully designed bridge is not something that they could have built a half planned out bridge, sent some cars and people over and seen if it held up, if it did what they thought it was. And so quite often, particularly in the case where we deal with large engineering projects, very expensive engineering projects, or ones that deal with people and their welfare and their safety, we really need to make sure we have as good of a theory, as good of rules or predictive constraints as possible. However, even for something as complex as building a bridge is, we know a lot about physics, but we don't know everything about the exact materials, how concrete behaves as precisely as we do know how, a perfectly frictionless car moving along a vacuum does, as a very classic physics problem. Very much a lot of engineering is solving math problems and calculating based off what we know best about these rules or these theories, but sometimes we're not given all the parameters, we're not given all the properties or all the equations that govern how something behaves, and we have to make some sort of estimate and some sort of assumption. At this point in most engineering problem design systems, we have to sort of grapple with the assumptions and constraints of our system. As I said before, engineers are very good at sort of looking up and trying to determine the constraints of their problem. Quite often when someone approaches you with a request to do a bit of engineering, they'll give you some specifications. These are constraints you must work within. Quite often they'll give you a budget and say these are the amount of materials or the dollars you have to spend on this, usually less than you would like. Of course, we work within the rules of science, within physics, chemistry, biology, and often material science. And there's also, of course, sort of the social constraints we place upon it, which may be sort of law-based. They might be permitting and zoning. They might be specific specifications that deal with environmental impact and things like that. And so these are things that place constraints on what we're able to do and sort of the creative design space we work within. Even with a lot of constraints placed on us as engineers, we're not really given enough to sort of perfectly predict what the answer must be. There's probably several valid, reasonable answers to these constraints, and we have to sort of make assumptions to fill in whatever might be missing. In many cases, the thing we deal most with is the idea of variability. When we design a bridge, or the engineers designed the Zakim Bridge, they had to sort of deal with the variability of temperature. Boston gets very, very hot and very, very cold, very wet, very dry, all of which changes the rules of how those materials behave, those fundamental properties. There's nothing that says that Boston is going to have a particular pattern of weather, and this variability in the conditions that the bridge will be subjected to requires us to often operate with some sort of margin of error, some flexibility that assumes usually the worst case scenario. Still, we can't sort of err too much on the side of safety. Otherwise, you would have a terribly large bridge that could survive really the end of the world, but would be very expensive and probably not look very nice. And so we're going to practice today, and we're going to try to explore within a relatively safe, low-stakes example how we deal with both the constraints of physics and other material constraints placed on us, but having to fill in the missing gaps with some assumptions of our own. So we're going to be answering a solicitation from the Department of Penny Transportation that requires two different vehicles to be built and constructed. We're going to first build a boat, a very small scale boat that's going to act as a ferry that takes people across the Boston Harbor. And the second, we're going to design a parachute system that's going to carry people from the top of the Prudential Center down to street level, of course, trying to slow their descent as much as possible. Now, of course, building any system is quite expensive. We can't really, the MBTA wouldn't just build a train and then put it on the tracks and then see how it does, in theory. So we really have to be able to predict how our proposed vehicles will perform, be confident that they're safe and that they're not going to let our coins or our pennies fall into harm, as well as meeting our specifications of trying to carry a certain number of people at a certain rate and clip. So a lot of our work is going to be trying to make sure that the one boat that we build performs exactly as we think, plus or minus a margin of error. Some of the constraints we deal with, of course, are going to be placed on by the materials, time, and budget of our system. But of course, we must deal with the physics of it, the physical laws. And the one most relevant towards our boat, or really anything that floats within a liquid or gas, is the opposing forces of buoyancy versus the force of gravity. These are constraints. These are constraints we have to deal with. Much of which is going to be given to us, some which we may have to estimate. And quite simply, as a little bit of a review from what we probably have encountered in physics, the reason why things float is that there is both, of course, the force of gravity, the weight of the boat, plus its cargo, so the passengers, which is going to be our mass times its gravity that pulls in the downward direction. And this is displaced, or rather, this is resisted by a buoyant force that comes by the lower density of basically an empty air-filled boat. Whatever submerged or volume displaced by that boat or balloon or whatever it might be gives us an opposing force, again related to this force of gravity. Very much simply put, our constraint is that our buoyant force must be higher than our force of our gravity. And of course, when the boat sort of sinks and finds its level in the water, these forces are going to be exactly equal and opposite. So we have to deal with this law, and we have to use it to get as close to a precise exact answer as we can. We can simplify this, of course, and sort of recognize that the same g, gravitational acceleration constant, is the same for both. And so we have a much more simplified look of these opposing forces that relates to the density of our liquid, in this case water, the volume of our boat that lies under the water level, and of course the mass of that entire system. So we're going to need to use this to be able to predict how our boat will perform, and we want to be very precise and accurate. The second sort of governing constraint we have to work in, or gives us at least a little bit of a guiding force, is going to be the drag that a parachute will exhibit as it falls down from a certain height. This force of drag does have a governing equation as well, which relates a drag coefficient, which is very much an experimental empirical guess about how the force relates to the area of this parachute. There's some general guidelines, but we have to make some estimates on what that drag coefficient is. The density, the speed of our air, mainly influenced by how quickly our parachute is falling, and of course the size of our parachute. Now, because this equation is a little more complex, and we don't assume a particular level of calculation skills yet, we can use this not so much as a equation that we can calculate exactly what this force of drag is and how long our parachute will take to fall, but we can use it as really a scaling relationship that tells us as we increase one parameter or decrease, how does our system respond, and ultimately give us something to maximize or optimize towards. And so looking at these things, our force of drag and really the parameters we as engineers can change and affect are going to be the drag coefficient, which is very much related to the shape of that object moving through the fluid. This drag coefficient, of course, is also used when you design cars and things moving, which you want to reduce air friction and air resistance, plane wings and other aerodynamic structures. And of course, the size or the frontal area, basically the area of the profile presented to your falling or moving direction. And so this equation we can reduce from something that's very, very precise, which even then is going to be an estimate because of this sort of hand-wavy, very empirically derived drag coefficient, to a scaling relationship in which the force is now proportional to these two factors, which we can change in our design, in our engineering designs. This type of relationship, this type of constraint, doesn't sort of set the same requirements as the buoyancy does, but instead gives us a direction to head, a way to optimize towards the highest drag force we could possibly get. So in addition to those physical design constraints, we of course work within very practical financial and of course time constraints. For this particular exercise, appropriate to the size and scale of these two things, our time and budget will be that we will have 30 minutes, no more, per round to design several vehicles, and we'll say what each round consists of. So we have to be efficient with how we plan, how we calculate how our vehicles will perform. We'll then have 30 minutes to construct to make sure that not only do we theoretically design a nice vehicle, but that we have the patience and sort of attention to detail to build to our specifications, to our own specifications, and something that will survive these other design constraints. Within the specifications by our Department of Penny Transportation, our boat is going to be constructed out of just a 6 by 6 inch piece of aluminum foil. No more. You are welcome to use less if you like. But we have material constraints. We have a type of material, sturdiness of material, and an amount of material. This boat, constructed out of this one piece of foil, has to carry at least 30 coins. And just like people are variable in how large they are, how much stuff they carry with them, our coins are also variable. It will consist of a mixed population of pennies, nickels, and dimes, some larger, some smaller, but we'll count out 30 coins or 30 passengers. And accordingly, of course, this is Boston Harbor, which is not the worst sea conditions, but not placid. And so we must not only construct a boat capable of carrying these coins, but it has to withstand some sort of rough conditions. And as the environment is quite variable, what rough conditions mean is something you must estimate and build in some margins of error and some safety margins for yourself. This boat also needs to be able to act as a more than one-time mode of transport. So we're going to load and unload your boats 10 times. Each time, we may have a different distribution of coins, of population, a different loading of where they sit in your boat, all creating variability that we have to make some assumptions about and potentially learn iteratively. This also implies our boat has to be quite sturdy to handle some manipulation. For a parachute, we'll construct them out of plastic bags. I have sort of 30-gallon plastic bags. That's all that there is. So from that, you must construct your parachute, whatever thing holds your coins. For this one, we'll set a standard payload of 10 pennies so that sort of everybody's dealing with the exact same payload. And we require, for reasons of safety, that it take about 3 or more seconds to drop it from essentially the height of the ceiling. We'll stand on the table and we'll sort of hold it to the ceiling and drop them, and that should take ideally 3 or more seconds. We'll also designate a landing area, since parachutes or any mode of transportation should get where it's going, and so we require both for the performance of our parachute, but also some of the accuracy, of which, again, we introduce variability, which we have to account for and try to engineer towards more or towards less variability. Because engineering is iterative, I don't expect you to necessarily get it bang on the first time. We're going to run this through a couple rounds to give ourselves some different tries. We're going to be doing this as team activities, so we'll split into we'll split into 2 teams, groups of 3. We'll shuffle between rounds so everybody has a chance to work with each other. This is our very small, nice, intimate engineering class, so it helps to get to know each other, both as sort of engineers, but feel free to sort of get to know each other as personal people. And we'll shuffle so everybody has a chance to sort of work with each other. So here's our rounds. We're in 2 rounds of boat design and 1 round of parachute design. We may do more if we require more attempts. But in the first boat round, we're going to work within relatively narrow constraints, trying to not have as many assumptions. We're going to sort of artificially control as much as we can to help us test and help us design better and understand how these forces play out. So we'll have a load of exactly 10 pennies, 10 dimes, 10 nickels to help give us some estimate, to help us better predict the load. You'll design a boat. You'll work together. Importantly, you will calculate where that boat sits in the water. You're going to design your boat however you seem fit. You're going to calculate those forces, make reasonable estimates as necessary, and you're going to essentially call your shot on the boat. You're going to indicate, drawing a little line, where in the water that boat is going to sit. It'd be crazy if people designed boats and didn't know how high or how low in the water they sat. So you need to make some good estimates under relatively controlled conditions. We'll put sort of a ½ centimeter margin of error on each side of that line in case some of your assumptions are higher or lower. But if you can design your boat and it doesn't sink with this payload, and you are able to hit your estimate, so good calculations are required, you'll get 4 out of 4 of those points for today's activity. We'll switch up our teams. We'll shuffle people around so everyone has a chance to work with each other. And we'll do a round 2 of our boat, which is going to be much more representative, introducing more variability, requiring more assumptions. We're going to have a variable mix of different pennies, nickels, and dimes, ultimately chosen randomly, as people randomly decide to take your public transit or not. We will sort of hit the same number of 30 coins, but again, a different mix based off of the population of pennies, nickels, and dimes that exists in this city. Here, we will make sure that your boat can hold at least these 30 coins. We'll subject them to some rougher conditions, which hopefully they don't capsize, as well as 10 loading and unloading cycles. So durability and this margin of error does matter. If your boat can survive being loaded 10 and loaded and unloaded 10 times, you'll get sort of full points for that. We will award a bonus point to the design that can carry the most pennies. Probably many more than 30, but we'll see how it goes. We'll switch one more time, and in the final third round, we'll design our parachutes. Again, we'll drop them from a standard height. All you have is this plastic bag from which you must construct all your parts. There's no tape, there's no string, there's no rubber bands to hold things together. So everything must come from this one material. So plan accordingly. You have one plastic bag. So planning is usually the thing that saves you in the end. We will drop them all from the same standard height, essentially the height of the ceiling. Your constraint, the parachute must land in the sort of 2 by 2 foot target we designate on the ground, and it must fall for at least 3 seconds, hopefully more. For that, you'll get all the points for this particular activity. And again, we'll award a bonus point for the one that lands or takes the longest to land or has the slowest descent. So, some good calculations, some good engineering design, and margins of error to get sort of full points for this activity. And of course, everyone's going to good chance of walking away with some bonus points so that you walk away with some bonus points. I do require, before I turn over materials to you, that you present and justify to me your design and calculations. Helps me check to make sure that you are headed for success. So things that you'll have to estimate, and you as a group will have to use, one, your best judgment. You can also look things up. You can also do a little bit of research to help you inform your designs. Rough water, rough environmental conditions is a variable thing that no one will be able to predict for you. I will say that our test chamber is going to be this tub filled roughly to the top with water. So whatever rough might mean within this thing, that's what rough conditions we will deal with. You'll have to sort of figure out how low do I feel comfortable letting the boat sit in the water. Obviously, you can load it so that water rises to the very, very top brim, and you get a lot of pennies and a lot of dimes and nickels in there, but it doesn't give you a margin of error in case something rocks or tilts that boat. You'll need to estimate how heavy is my payload. These are good things to look up, and there's better and worse numbers out there. How heavy are each of my 3 types of coins? And of course, trying to estimate what is the likely random population of 30 coins I'm going to get. That you'll need to make some estimates, and I can help you think through how we make those estimates. You're welcome to try to specify how your passengers will load into your boat, but as you well understand, people don't always follow directions, so there's going to be some variability in how they decide to stack themselves in your boat. So something we as engineers must design for to help compensate for people undoubtedly not following directions. Some hints about how boats work and some better boat designs that maybe you might not think about. These boats particularly do not need to be hydrodynamic, so they don't need to be able to move very quickly through the water. They just need to be able to float. Make sure you build in some safety margin, some room for error in case the boat moves. Our boats also need to survive handling and movement and loading and unloading, and so they should be rigid. They shouldn't crumple in on themselves, and they should be pretty puncture resistant to holes and tears and things like that. I will give you a hint that aluminum foil is not terribly strong. It's easy to poke holes in. If there's a hole in your boat, of course, it's going to sink. Your parachute of course, has these opposing forces, and generally, the larger the parachute is, the slower it will fall. But of course, the larger the parachute is, the heavier it will be. So make sure you're designing a parachute appropriate for the 10 pennies that will be carried. A lot is going to require you to discuss amongst yourselves what information we know, what information we need to estimate and fill in. And of course, we'll do this in a couple rounds, so we have a couple tries to get it right. I will leave up sort of some of the governing equations, of course, the design constraints to help us uh, design better versus worse things. But we will do this, of course, in our 3 rounds. 30 minutes to plan, discuss, research each round. 30 minutes to design, construct, and build. If you're confident before then, we'll start earlier. But that is as much time as this challenge has allotted you.